Are you able to see the screen?
Sir.
Okay. Yeah, so welcome back to this session, and we'll quickly start from where we left yesterday. So we have seen yesterday that the relevance and importance of analog IC design and the concept of analog things, and we actually came closer to why we go with the device, which is typically the MOSFET. Now, when we know that MOSFET is very important, so that becomes very important in understanding how MOSFETs work. So, although you guys might be aware of these things, but let me put it in a nutshell how exactly the MOSFET is going to work. Now, again, this concept you should be such clear that whenever someone asks, whether it is in an interview or in a discussion, you should be able to explain the entire operation of the MOSFET in an quick and understandable manner with the help of these particular points, whatever I'm going to discuss right now. Right? So straightforward, let's jump into the MOSFETs. Now, like I told, MOSFETs are your transistors, the one category of transistors which are being most relevant and used since 1960s, that since its invention, and they are prevailing till now due to its huge advantage with respect to scaling and due to its capability of working at extremely low and extremely high voltages. Now, when I say that when they are going to work at extremely low and extremely high voltages, what exactly we mean by that? So that also we need to understand where exactly we are applying voltage and how is that it is going to take the voltage. So all these things we are trying to understand. Now, when we say that we are going to apply some voltage and we say that it is going to some current is flowing through the particular MOSFET, where exactly this current flows. So to understand that, we should be first knowing the structure of that particular MOSFET. Now I'm going to draw the cross section. When I say cross section, if I cut that entire MOSFET and in a 2D two-dimensional view and try to view it, how exactly it is going to look and what you are going to see. So I'm going to see something like this. The MOSFET is usually, these are your planar MOSFETs. So you will usually see something like this, where you have two, I can say, trenches over here, where you see, we usually call them as a well in MOSFET technology, and then you have some sort of these connections. I'll name them what exactly they are. So there would be something like this structure, and let's say this is as of now I'm not going to define what kind of MOSFET it is and how exactly I need to identify these MOSFET. So let's do that sometime later, but this is how the cross-sectional view of that particular MOSFET looks. Now we also know that the MOSFETs are typically classified into two types, and everyone is aware of that. They are basically NMOS and PMOS. Sometimes they are also being categorically classified as enhancement and depletion type. Now, how do I identify all those things and which are more important and why these are named that way? Let's try to understand along with some sort of simple working. So that would be our entire objective of this session, which we are going to go through it. I'm not going to drag it for a longer duration, like for 2 to 3 sessions. It will be a quick recap because we all are, as of now, we should be aware of these things. Okay. Now, when I say NMOS, it means N MOSFET, or what does this N stands for? Anyone? N stands for N type MOSFET, we say, but what is this N type in this entire MOSFET structure? Where do you define that N that will justify this name? N.
Channel, sir. N channel MOSFET.
Exactly. Now that is basically N channel or N type channel. Now, how do I identify that, and whether it is an N channel MOSFET or N type MOSFET, whether it is an enhancement MOSFET or depletion MOSFET? Let us try to understand from this particular quick working. Okay, I'll come back to this entire definition as and when we try to understand this working. So basically, MOSFET, we say it as a three terminal device, but actually it is a four terminal device. Please do remember. Now, in an interview, whenever someone asks whether it is a three terminal device or a four terminal device, three terminal device is something which normal guys tell. Four terminal device is what should be your answer, and you should justify what is your fourth terminal and its importance. Now we try to understand where is my fourth terminal and what is that fourth terminal and why it should be connected that way. Maybe in some of the maybe the students in their seventh and sixth semester or fifth semester, if they have done some laboratory experiments, they would have seen that fourth terminal would be connected to either VDD or power supply or to ground. Now the question is why, that also we'll try to understand. Okay, so what are those three or basically the four terminals? So I have this particular terminal. So this is basically my metallic connection through which the terminal is extracted. That is basically my source, drain, and this would be my gate. Now, a lot of things to understand over here. MOSFET is basically a symmetrical device. Symmetrical device is I can interchange source and drains. That means I can name the source and drains accordingly, or in the due course of working, based on the voltage, your source and drain would get defined. There is no fixed source and drains, but normally as per the convention we go with this way. And normally as per the convention, when we talk about the NMOS or PMOS, then we define something called a source and drain as per those convention. We'll talk about that. Now, when I have defined these things, so this particular thing is my metal, and I have here the dashed part is my oxide, and let's consider this entire bigger section is made up of P type material, and I'm going to call it as P substrate. Sometimes it is also called by the name body, just like your pizza base on top of which your entire structure is getting created. Now, if I have P substrate over here, usually I'll go with the N type material getting doped over here, or N type material being pushed in over here in this small region. And the reason of telling N plus here indicates that it is not negative and positive together. It means plus here indicates heavy doping. Heavy doping in the sense more electrons or more negative charges. That is the indication of plus over here. Don't get confused. So that means within this small area, a lot of charges are being pushed over here. And in this area, I have the P-type material. So there goes my structure. So because I have metal, I have a oxide, and this is my semiconductor material. Hence the name metal oxide semiconductor. And there is something called as field effect transistor. Let's try to understand where this field is created, what kind of field is created. And usually this is the transistor which is going to transfer the resistance from one end to another, and we call it as metal oxide semiconductor field effect transistor. And usually the field would be created beneath this oxide layer, which we are going to call it as a channel. So let us try to look into that aspect. So now I want to just So let's say that I want to, let's redraw the structure one more time quickly. Now let's try to apply some voltages and then figure out some sort of operation, and then we can define. Anyhow, we have now defined the three terminals. We have seen what are the three terminals: source, gate, and drain. Now always remember, you have to be very specific in understanding these things. Forgive me for my bad drawings. Okay. Okay, let's try to apply some voltages and then figure out whether it is an enhancement type or depletion type of MOSFET quickly. Yeah. So let us try to apply some sort of voltage. Now, since there are three terminals, I could apply two set of voltages that usually that we go. Now, let's try to apply all sort of voltages. Now, again, this is one of the very interesting thing that your entire interview process would start with: define and explain the working of MOSFET. And that is where you have to ensure that you are completely cutthroat in explaining all the aspects of the MOSFETs. Okay, now when I apply some voltage between, these terminologies are very important. Voltage between gate and source, we call it by the name VGS. That's it. Now, why I didn't call it as VSG? Because gated is at positive terminal of my battery. I named that particular G as my first term, VGS. When something is called by the VSG, you just ensure that VSG means AC is at the positive terminal and G is connected to the negative terminal of the battery. So that is the indication. Now, as of now, let us not apply, I'm not going to apply any voltage between the drain and source. I'm going to keep it open. I mean, I'm not going to apply anything. For time being, I'm just keeping like this, ready for applying the voltage. But right now, I'm not going to apply. Now, when I apply just VGS, let's say that let VGS equal to 0.1 volt. Now, when I apply something like this, so what is going to happen over here? Now, 0.1, what is your voltage? Voltage is basically your stored energy or stored the amount of charges that are being stored. So 0.volt equivalent amount of charges are being pushed to the top of your gate. That means, let's say that 0.1 indicates these number of positive charges, and similarly 0.1 amount of equivalent negative charges are being pushed into this particular small region, which is your N plus. Now, what is going to happen at source side? Of course, there is an N plus region over here. There would be some space left, and these electrons would get pushed and they sit over here. But what is going to happen to the gate side? These positive charges, they come and sit on top of that. Now tell me whether these positive charges, will they enter inside the MOSFET or not? Whether they will enter inside the MOSFET or not. The answer is the MOSFET will not allow these charges to flow or these charges to penetrate inside the MOSFET. The reason is because of this oxide layer. You can see there is an oxide layer, right? Oxide is nothing but sometimes this oxide is also called by the name polysilicon. Polysilicon is nothing but purest SiO2. But what is your SiO2? Silicon dioxide. So that is basically the oxide that is being used. And what these oxides are? These are basically insulators, and insulators doesn't allow any flow of current. And because it is a purest insulator, its insulation capability is very high. Very, it will be very high in the sense there will be almost zero electrons that will be entering over here, because there should not be any electrons that should be flowing through the gate. If that flows, that means there is a gate current. Basically, what does that mean? Whenever any charges flow, What does that mean? There is a current flowing. So I should not allow any amount of charge to flow inside or penetrate within this particular MOSFET. So these positive charges, they come and accumulate over here. Now, I have not applied anything over here, so let's not to worry about these things. Now, like I told, MOSFET being symmetrical device, what would have happened if I just reverse this polarity? In the sense, if I applied the voltage between gate and drain, then possibly this would have worked as a source and this would have worked as a drain. As simple as that. Then in that case, my voltage would be applied between again gate and source, and my right side portion would be my source and left side portion would be my drain. That's why it is a symmetrical device. Fine. Now what is going to happen over here? When this amount of charge come and sit on top of the gate, it is going to first thing, these charges, these positive charges, repel negative charges. Where do they repel? You see, there are a lot of positive charges that are present over here, right? So initially, positive, they repel, and then positive, negative, they attract. Right now, there are plenty amount of positive charges, and because 0.1 amount of positive charges are sitting over here, they repel these positive charges, something like this. And when that happens, there is this empty region that is being created. No charges initially. Please remember this. And this particular condition is known as, and this particular mode of operation is known as depletion mode of operation. And very important thing, this depletion mode of operation doesn't have any relation with the depletion type of MOSFET. Don't be under that impression. This is a phenomenon that is going to happen in enhancement type MOSFET as well as in the depletion type MOSFET also. But why we call it as a depletion mode? Because this region is depleted of carriers or depleted of charges. What is depleted? Depleted means no charges. Depleted of, I say carriers or charges. Carriers in the sense charge carriers. One and the same. So this is going to happen for a very, very small amount of time, for small duration. This is going to happen for a very small duration of time. You'll not get a time to even visualize that. It so happens that when you apply some voltage, positive voltage, it will repel those negative, these positive charges towards this body, Now, in the meantime, immediately, it is also going to attract the negative charges, isn't it? Because there were these positive charges, and the very basic nature of these positive charges is to attract the negative charges. And where do you think the negative charges are being attracted? You could see over here, this P substrate, what are the majority carriers? They are P. And what are your minority carriers? They are N. Always remember, when I say P substrate, until and unless I say it as an intrinsic material, that means it's the purest material. It means that it will have, or it means that it's an extrinsic material. And what is very intrinsic and extrinsic material? When I say intrinsic semiconductor, it's a pure. Extrinsic semiconductor, it is doped with impurities. Now here, since I have not mentioned, I just mentioned it is a p-type material. That means it will be doped with some small amount of negative charges. So that means there would be small amount of negative charges that would be present over here, and also there are some negative charges present here also towards the source and drain. But of course, they are just a little bit far apart from these positive charges. So they may not entirely get dragged to this beneath this oxide, but the charge carriers or the minority charge carriers, which are your electrons, which are present just beneath this oxide layer, they gets attracted. And now you could see that 0.1 equivalent amount of electrons or the negative charges, they get attracted and they just sit beneath the oxide layer. Now here comes the beauty. The amount of voltage whatever you are applying decides the amount of electrons that are being attracted. Now this phenomenon, now if you increase VGS, like for example, if VGS is increased. Now, these are some of the trick questions that are usually asked. What is going to happen when certain amount of voltage is applied and you increase this voltage? What is theoretically it is going to happen? So you should be aware. If VGS is increased, more positive charges sit on gate and it is going to attract more negative charges beneath oxide. As simple as that. Now, this is basically the benchmark in the creation of what is known as channel. And why we call it as a channel? Channel is the name that has been given, which is going to link the source and drain together, something like this. And that is the reason why we call it as a channel, right? So when this is going to happen, we say that the entire MOSFET now has got the channel being created. So now let me just take this picture. Let me just reuse it over here. Okay. Yeah. So now, okay. So let me just rub all this portion. So now that we know that this channel is being started to form. Now, the question is how exactly it is going to help for my conductivity, or basically how it is going to act as a device which is going to ensure the current is flowing through it. Yes, as you all know that now this particular action, when you start increasing, so VGS increases, strength of channel increases. That means if I keep on pushing in more and more amount of positive charges, that means if I'm increasing VGS, it is going to ensure that more amount of negative charges are being attracted beneath the oxide layer. Now, this entire scenario, initially it would be haphazardous. That means, see, basically whenever something happens in the channel, let's say that I have so usually the electrons starts attracted something like this, and then they slowly and steadily align themselves uniformly to create the channel. Okay, so now the question is till what time should I increase VGS? So at what voltage should I stop? So where to stop increasing VGS? Now there is something called as threshold voltage, the concept of threshold voltage. That means, see, basically it is going to act as a bridge between source and drain. So let's say that you are constructing a bridge between point A and B. And when you stop constructing the bridge, when you feel that the bridge has been constructed properly with all the strength, and now your vehicles can move from A to B. So that is when you stop constructing the bridge. Otherwise, there is no point in, otherwise you keep on constructing the bridge, right? So here also the same thing. Now here, it is defined with the help of this threshold voltage. That means every MOSFET, when you buy it from the vendor, it comes out with some of the specification called as threshold voltage defined as VTH. Let's say that if VTH is 1 volt, that means till 1 volt or slightly greater than 1 volt, you should apply your VGS. That means till VGS is greater than or equal to VT, should apply that VGS. That means if your till the VGS is greater than that particular threshold voltage or slightly greater than that voltage, we should apply. That means let's say that I have applied VGS equal to 1 volt. Now ample amount of electrons are being attracted, and now that the channel is being formed. Now the question is how the current starts to move, how the entire operation starts to work. Now to understand that, now if you see over here, I'll give one analogy. Let's say that you're constructing a bridge. Now, while constructing the bridge, the workers usually walk from one end to another end, or they usually walk on the bridge and then they do the construction, isn't it? So similarly, when this channel is getting created, when this bridge is getting created, which we call it as channel, there are some amount of electrons that are moving from here to here by default. And that means even while only VGS is being applied, there is still small movement of electrons from this one end to another end, which is from the source end to drain end. That means a small amount of current would be flowing from source to drain. So that is one thing. But I'm not relying on to those things. I want to ensure that some good amount of current flows by pushing in some extra voltage. And there comes your this particular voltage, which is your VD. Yes, again, D is connected to the positive side of the battery. S is at the negative. And again, the reason is I cannot connect it this way, right? See, again, if I would have connected it this way, is absolutely a nonsense thing, right? Because see, the source, you say at one side you say source is connected to the negative potential of the battery, and here you say it is connected to the positive potential. So it is really a mismatch in the potential. So I cannot do this way. So wherever your source potential is tied, the same source potential is tied for this drain and source terminal also. So this is my VDS. Now, since I have stopped increasing VGS, so VGS, let's say VGS equal to 1 volt, stop increasing it. Now apply VDS and start increasing it. Let's say that I start applying VDS from 0.1 volt. Now again, the same phenomena. What is going to happen? Now this is the voltage, or this is particular the thing where a lot of different phenomena are going to take place. When you apply this particular voltage, again, zero point 0.1 equivalent amount of electrons, they come through this wire and they get accumulated in this source region. And 0.1 equivalent amount of positive charges, they come and they sit on this metallic layer. And again, sometimes through this metallic layer, because there is no oxide layer, they may go inside this N plus region and some neutralization may happen, right? So all those things are there, but in due course of time, this is basically your positive charges are sitting over here on top of this metal layer, and there is a negative charges over here. Now, very interesting things that are going to happen over here. Let us try to understand that. Now, when you apply this voltage, again, till what time should I apply this voltage? There is at what voltage should I stop increasing VDS? Is there any end? So to understand that, I keep on increasing VDS. Now I keep on increasing this VDS such that a point reaches when this small region, this small N plus region would not be able to hold those electrons within this small region. And now, because you have increased this VDS, so let's say that VDS is now has reached 2 volts. So this 2 volt amount of electrons, which is a lot of electrons, they cannot withhold here within the small region. Now they hop outside. Hop outside means They may come here, they may come here, they may reach over here. There is all possibilities. You should be thinking of that as well. There is every possibility where they can come out. Few electrons, they come here, they get neutralized. That's fair enough. But few electrons, which I am concerned, they hop into this channel. And because in the channel you have the electrons, which are negative particles, and these are also the electrons, which are the negative charges from the source. These negative charges, they repel each other. That means the electron which has jumped over here, it gets repelled and get moves over here. It gets repelled and comes over here, get repelled, and finally it comes and it just reaches the drain region. That means now the electrons from source to drain have traveled. So there is a movement of charges, and whenever a charge moves, I say that there is a flow of current, and this is how the current starts to flow. That means the major voltage which ensures the flow of current happens is first VGS, because without that bridge or without the channel there is no flow of current, and then it is VDS. Now, the equation is very simple. You increase your VDS, that means your entire current starts to increase. So, let's say I'm just replicating the same thing. So, if I start to increase this VDS, let's rub all these things. So, I have applied something like this. I have reached a point of 2 volts. Now, this thing, till what time should I apply the voltage? At what voltage should I stop this increasing this VDS? All these things we'll try to visualize in terms of simulation. We'll try to understand that. But the condition to increase VDS. So basically, there are two conditions. One is if VDS is greater than VGS, and if VDS is less than VGS. That means, let's say that VDS is 2 volt, and let's say that VGS you have applied, what was your VGS? VGS you applied at 1 volt. What is going to happen? And VDS is less than 1 volt. So this is my case 1. I'm going to consider another case. Let's say that VDS is greater than VGS and VDS less than VGS. I'm going to consider 4 volt greater than, let's say that VGS is 2 volts and this is, let's say, 1 volt, and it is less than VGS is 2 volt. Yeah. Now, of course, as you might be aware that there I should add one more potential over here, which is VGS minus VT. I'll try to add that particular value. So basically, it is always VGS, it is always VDS greater than VGS minus VT, or it will be VDS less than VGS minus VT. These two are the conditions which are going to define your current flowing capability, and these are the two conditions which are also going to define your region of operation. Here I have not taken VT for simplicity purpose. Here I have included VT. Now why I am subtracting VT? Because see, usually when you are constructing the bridge, and during the construction, like I told, there are the movement of workers, and you cannot claim that the bridge has already opened for the general traffic just by seeing the workers walking on the bridge, right? Those workers are walking on the bridge to ensure that bridge is getting constructed properly with a full strength. So I cannot claim that those movements are a genuine movement of traffic on the bridge. Similarly, I cannot claim that while the channel is being getting created, whatever the electrons are being moving from one end to another end, I cannot claim that that is my actual current. And that is the reason that amount of voltage would be subtracted from your VGS, just to ensure that whatever the voltage I wasted in creating, or whatever the voltage I spent in creating the channel, is ignored from this particular VGS. So that is one thing you should remember. Always remember why I subtract VT, because this VT amount of voltage is initially used in creating the channel, and in no way that it is going to serve that because of this VT my current movement is happening. So that is the reason why I usually subtract this VT term from my VGS. So these two things are going to define my region of operation, and let's try to understand these two with some graph. And when I try to understand this with a graph, it has to through the simulation. I'll keep it with a simple experiment. Maybe in the subsequent session, we'll try to understand what is going to happen by applying these voltages. Now the question is, now you have applied VDS. Let's assume that I'm stopping. Let's assume that I have applied VGS equal to 3 volt. I told it should be greater than the threshold voltage. And let's say that I have applied VDS as 6 volt, and I stop increasing both VDS and VGS. So that means whatever the VDS I applied, that 6 volt, that much equivalent amount of voltage would give rise to my current. And the current that flows due to VDS is basically known as your drain current. It is conventionally, the name has been given that way because the current flows from source to drain. Here the electrons move from the source to drain, and that is as per the movement of charges, these negative charges are moving from source to drain. But if I consider the other way around with respect to the charge moment concept, it is the positive charges that would be moving from drain to source. So let us not get confused about that. So drain current is the name, convention name that has been given, but the current actually flows from source to drain, and it is being denoted by the term ID or ID or ID, in whatever manner you can mention. So that's my drain current. So this is basically how exactly your entire current starts to flow. Now remember, I told there was one more terminal, fourth terminal, along with source, gate, and drain, and that terminal is called as body. This substrate, whatever I'm showing here, right? This is my fourth terminal, which is my body terminal or a substrate terminal. Okay, now where should I connect it? And that depends on what kind of MOSFET it is. Now, can anybody tell me quickly what kind of MOSFET it is? Of course, it's an N-channel MOSFET because channel is an N type because the channel is made up of N type of material. Always remember, when I say something as NMOS, I'm talking this N with respect to channel. It is it is going to define the nature of the channel, not the substrate. So this is N type MOSFET, means N channel MOSFET. Now, can you tell me whether it is an enhancement MOSFET or a depletion MOSFET?
And enhancement type MOSFET.
Enhancement. And may I know the reason why? See, the reason is,
because
yeah, please.
because we have enhanced the channel by applying VGS, which
Exactly.
is greater than VGS.
Exactly. There were no channel, and you have just enhanced the channel. You have just created the channel, and that's the reason this becomes N channel enhancement type MOSFET. Done. And the same example or same explanation holds good for your P channel enhancement type MOSFET, where you just interchange all the polarities of your source, drain, and substrate. There you will be taking the N type substrate, and your source and drain would be of P type material, and you would be applying the reverse voltage on a quicker note. That's very important. P-type MOSFET. Most people, we usually ignore the P-type MOSFET, but that is where the trick is there, because all the voltages would go the other way around, and you should be able to even visualize the p-type MOSFET as well. So I'll just simply, for simplicity, I'll just consider this one. See, because you already know that the p-type MOSFET should have p-type channel over here. The channel should be of p-type material. So in order to have the p-type channel, your applied voltage must be negative voltage here, and that's how you should be able to identify. Because if you apply the negative voltage, negative charges will come and sit over here, and it will attract the positive charges. And this is my, see now how you're going to name it. See, VG, if you name it as VGS only, how your VGS would look now? Negative, because G is connected to the negative supply of the battery, and S is at your positive supply of the battery. Always remember, see, these are some of the nomenclature which most of the textbooks use, and sometimes it is very confusing also. So if I use this nomenclature, see, if I use the same nomenclature VGS for both N and P, what is the difference? If I use VGS for N-type MOSFET, my VGS would be always positive. And if I use the same VGS name for my PMOS, it would be always negative. That means, see, when you analyze your PMOS, your analysis would go with respect to the negative voltages. When you analyze your NMOS, your analysis would go with respect to positive voltages. Now, in order to avoid this confusion, there is something they use, VGS for NMOS, it is positive voltage. Now here what they do, VSG for PMOS, that also now I can consider it as a positive voltage, because VSG, S, where is S connected? S is connected to the positive terminal of the battery. Now why I do this? Because in order to ensure that your all analysis are with respect to positive voltages, I can use this particular terminal. So they sometime write this way also, mod of that, even to avoid the confusion. Even if there is a negative voltage, you just consider it as a positive voltage and do the analysis. At the end, you just change the polarity of the current, because the current here is flowing due to the positive charges, and here the current is flowing due to the negative charges. So that is the nomenclature. Nomenclature wise, you can name it and you can analyze it in whatever manner you do, but understanding purpose, the concept is going to remain the same thing. So my concept, usually we go with the N-type MOSFET and do all the analysis. Fine. Now I was talking about this particular fourth terminal body. Where should I connect? Now usually your body is connected to the source of your MOSFET, and typically, if I talk about the symbols, there are multiple symbols. This is of NMOS, and then I have just like this, right? Both are NMOS. And if I go with a PMOS, the arrow mark changes, and usually in the digital systems we go with this bubble logic, right? So normally in all your and the more effective symbol is your this one. So here it would be, and this is your body, and that's your body. See, normally, like I told here, it is assumed that the body is being taken care in normally your digital examples or wherever you see. But actually, when you do the real-time examples, when you take the real-time MOSFETs and do the simulation, you have to take care of your body terminal also. Now, if I consider this particular NMOS, and if I say this is source, drain, and gate, And again, if I consider, let's say that let's consider source, gate, and drain, and let me name it as, I'll just tell you why I'm naming it that way. There is a reason for that, right? So if I do this way, so this body has to be connected to this source terminal whenever we talk with respect to NMOS, and this body has to be connected to the again the source terminal, because my source terminal is here for my PMOS. The reason why, what happens if I don't connect this one, that is one thing we should address, that I'm going to take it in the next session. And another thing, if you observe over here, when you are working onto this MOSFET, if you slowly and steadily observe, there is a peculiar action is happening over here. If you see, this is your entire p-type material here in this region, and this is your n-type material. So that means, see, one is Y body tied to source only. Why not something else? Or specifically, if I say, if I consider my, so if I just consider my NMOS, body is connected to the most negative potential of your entire MOSFET, and the most negative potential is, as of now, it is source, and that's why I call it as a source, right? So why, what is the reason behind that? We'll try to address that. And another thing, if you quickly observe over here on a quicker note, these are the two very important questions, the concepts you should be able to understand. Sorry. So there is a channel over here, and now this is your p-type material, and this is n-type material. And if you observe over here, there is this particular junction, and you have p and n, and here where is your voltages are being connected. This is connected to the positive side, and I told body of your, or the substrate of your MOSFET has to be connected to the most negative potential, which is happened to be my source, and this is connected like this. So if I try to open up this entire structure, it looks something like this, where N is connected to the positive and P is connected to the negative. Now, if you observe, is it not looking just like PN junction diode under reverse bias action? How do you define the biasing scheme? Whenever your P side of whenever if your P type of the PN junction diode is at higher potential and N is at lower potential. See, if this is higher potential and this is at lower potential, obviously this would have been forward bias. But now this is at lower potential and this is at higher potential. So that means definitely it is reverse biased. Now there is an inbuilt, or I can say an implicitly built PN junction reverse biased diode that is happening towards the drain side of your MOSFET, of your N-type MOSFET. That means all the characteristics that you are going to observe in a reverse biased diode, that is going to be seen over here, and which you are supposed to address and which you are supposed to observe, and that is going to identify, or that is going to tell you what is the maximum limit of VDS that you are going to apply. Remember, I just showed you over here what was the limit of VDS, because here we were told that VGS you have to apply till a particular time, till my channel is being formed. But what was the limitation on VDS? So that limitation on VDS is being addressed over here. So this entire aspect of why we should tie body to the source or negative potential, if I consider my NMOS, and what is going to happen towards the drain side, which I can right now see there is a reverse biased junction, PN junction is going to happen. We're going to address all these things, which is something called as the concept of body effect, right? Which usually we call it as a second order effect. So all these things we're going to look into in my next session. So that's it from my end in this session. I'll just stop it for now, and then we can again meet up in the next session. So if you have any doubts, difficulties, you can let me know. Otherwise, we'll stop it here.